So what did we learn in the last class? Okay, so we learned a few important things about integrating analytic functions, right? So first thing we learned that if f of z is analytic, then integral z f of z is what? It is 0 for any closed curve, simple closed curve. Okay? Okay. So that was the first thing. And then we learned that if f of z is analytic anywhere, okay, then you can do an integral of the type z mapped to z2. Maybe we learned, okay, yeah, we showed this and then it followed that this is basically you can do this integral as if it was a real function.
Yes.
Right? You didn't need to care about the path. This integral was path independent. Okay? So basically if let's say g is the derivative of f, okay, then this was g calculated at z2 minus g calculated at z0. G of z, sorry, f is basically is dg by dz. So f is the derivative of g. I said it the other way around. Okay? So if f of z is dg by dz, then you put it here, then you get g of z2 minus g of z1. So the only reason you were able to do this was because your function was analytic everywhere. Okay? Then we learned that, okay, let's consider functions which have a single point of non-analyticity. Okay? And the function we took was f of z equal to 1 by z, right? Okay? And in fact we did a bit better, 1 by z to the power n, where n is some positive, right? Then we computed that it's integral over a loop, right? Over a loop encircling origin. And we concluded that integral over any loop containing origin dz by z to the power n is 2 pi I only if n is 1, right? We concluded that integral dz by z to the power n is 2 pi I only if n is 1, right? Otherwise it is 0, right? Okay? Good. Okay, let's consider this integral again. This integral. Now instead of doing it over a loop, okay, let me put some limits, some z1 to z2. How do I think of this integral? Okay, earlier we could just get away with it, right? We could just get away with treating it as a real function and doing the integral as if it were a real function, right? That's because this integral, the integrand f of z was what? Analytic everywhere, right? So path didn't matter. Okay. Now there is one point, right? Now there is one point. Okay. Now there is one point where the Cauchy-Riemann conditions don't hold. Okay. And the function is not analytic, right? Now, so which point?
Wait. 0.
It is okay. This is some new stuff. It is the point at z equal 0, right? This point, right? And let's say my z1 is here, and my z2 is okay. Now you can draw how many paths between z1 and z2? How many paths? Infinitely many, right? But they can be characterized in two categories. Okay? One, paths of the type this, which go to z1 and z2. Okay? Right? What do you think should be the other type of path? Huh? No. So there are infinitely many paths, right? But I can, all these infinitely many paths, I can divide them into just two groups. Okay? One group would be paths of this type. Okay? Paths of this type, paths of this type, or straight line from here to here, right? What would be the other one? Exactly. The other one, not include the other one who will go around z equal to 0, right? Who will go around this point of the point where the function is not analytic. Okay? Okay. So now, how do I associate values to this integral? Okay? Let's say I am some naive person and I just do this integral and I say, okay, I know integral dz by z is just log z. I think of it as a real function again and just do. So then this should be what? Log of z2 minus log of z1 or log of z2 by z1. The log function that we learned, okay? Okay, good. But then which one? But then it's not clear, right? Right? It's not clear that this value, okay? Which curve should I associate this value with? Right? Is it curves of this type? Or is it curves of this type? Why? Because I know that let's consider two curves which form a loop. Let's say I consider this curve, right? Okay, curve 1, okay? Fine. Remember, all curves of type 1 will have same value. Right? Right? Why? Because curves of type 1, if you take two curves of type 1, right, they form a loop, right? Inside that loop, the function is analytic. So the integral or the closed loop is 0, so that would mean the two paths should have, right, same answer, right? Provided the direction is compatible with the statement that you are giving. Okay, good. So and paths of type 2 should have the same answer, right?
Yes.
Because paths of type 2, let's say if I consider another path like this path, right, this path and this path, right, they form a closed loop and the function is analytic inside there. Whatever non-analyticity is there, it is there, right? Z equal to 0, right? Okay? So there are only two possible values, there are only two values that you have to assign. One, values to paths of type 1, right? You need to assign a value to paths of type 1 and assign values to paths of type 2, right? It is not that every path will have a different value now, just because there is a similarity as Z equal to 0, right? The function is non-analytic at Z equal to 0, right? It is not that you have to assign a new value to every path, okay? There is still it's much less harder task than that, right? The paths still don't matter. It's just that it would matter whether you consider a path like this or a path like this. There's just two values that you have assigned to these integrals, okay? Good. So let's see this path of type 1, right? This path, okay? Which goes from, let's say, Z1 to Z2. Okay? Good. So what is integral dz by z? Log z. Right? Now, if I track log z, because you have integrating what? Dz by z, eventually it is what? Log z. Right? If I think of it as a real function. So it means, basically, if I track log z, what happens to log z along this path? Okay? I don't see any funny business. Right? I just see log z, oh, continuous, okay, nice, analytic, everywhere on this path. Right? There is no issue. There is no issue. Okay? So I take this path and associate this value to it. Z1 from Z1 to Z2. There is a reason why I'm saying associate, assign. Okay, that will become clear in there. Z1 to Z2, and this gives you log what? Z2 by Z. I associate this value with it. Okay? Okay, good. Now what about paths of other type? Okay? What about paths of other type? Okay. Then paths of type 2. Okay? Fine. Okay, I didn't explain why I expect the answers to be different, right? Did I explain that? Probably not, right? So let's keep a pin on this and let's try to explain why the answers should be different, right? So if I add the integral on path 1, let me call it I1, okay? And integral on path 2, but the other way around, from Z2 to Z1, okay? What should I get? I should get 2 pi r, right? I should get 2 pi I because I'll get integral dz by z over a closed loop. Right? I should get 2 pi I. So the two integrals, right, can't be same. They differ by what?
2 pi.
2 pi I. Right? Right? They can't. If they are same, then the integral, then both the integrals should be pi I. But you know that the integral has at least depend on these points, the end points, right? These 2 points, right? It can't be a constant. It can't be a constant, right? So, but if it's not a constant, then the issue is the two can't be same, right? Two can't be same, right? So one has to differ from the other by 2 pi. Okay, by 2 pi. So that's why I'm saying that you have to associate different values to these two integrals. Okay, that's why. Okay. So one I associated an integral. So I associated a value already. Okay. I associated a value, and what was the value? Log z2 by z1. Why? Because on this curve, I don't see any funny business going on with log z. Right? Log z is continuous, whatever. Right? Yeah? It's well defined. Right? On this curve. Okay. Fine?
Yes, sir.
Okay. Now let's take the other one. What is the issue with this? What is the issue with this guy? Okay. If I track log z, remember what is log z? It is log r e power iota theta, which is log r plus iota theta. Right? So imaginary part of log z is what? Theta. Right? Yes. Now when you are going over part 2, this path, right? This path, the point of non-analyticity is here, right? You hit this positive line, right? Positive imaginary line. Huh? What happened there? What happened there? Theta just below is what?
Negative.
No, not negative.
Just below is
Okay, negative, but no. Okay, yeah, this is a good point. Why shouldn't I choose negative? But it will become clear later on. But first, I am telling you to measure angle from here, like this. So, what is theta just below? 2 pi. Right? Yes. So, log is an imaginary part of 2 pi. What is theta just above? Theta. No, just above here. This point and this point I am talking about. What is, let's say this is point A, point B, means infinitesimally close to positive real axis. Okay? What is theta at point A? 2 pi. What is theta at point B? 0. Good. 0. Right? The magnitudes are same because you are essentially talking about a point which is very close to each other. So magnitudes is just this length. But argument jumps, right? 0 to 2 pi. But that's not really a jump because it's the same representation, right? E power I 2 pi is 1. But for log that matters. For log that matters, right? Because log, the imaginary part of log is directly the argument. It's a linear function. It's not e to the power something. It's just linear function. Right? It just picks up the argument. Right? Imaginary part of the log. Right? So it means log sees what? A discontinuity. Right? Right? Yes, log sees a discontinuity. Okay? So I can't just integrate from z2 to z1. Right? What did you do in real functions when you were integrating and you encountered a discontinuity? Separate. Exactly, you separate. So I integrate from here to here and then from here to here. Okay? And I integrate like real functions. Okay? Huh? So integral over path 2 dz by z. I integrate from path 2, z2 to z1 along path, let's say, I don't know, whatever path. This doesn't matter, right? Because you can deform. Along whatever path, I should split it. The correct way to do it is to split it. Z2 to what? A. Z2 to point A. Right? dz by z. And then what? Point B to z1. dz by z. Right? What is this guy? What is this guy?
0.
Huh? What is this guy? This is log
of
z2
by A.
Sorry, log of A by z. Remember, A is a complex number, right? I have to be careful with the argument of A, right? A is essentially a real number which is infinitely close to the positive real axis, right? But I have to be careful with the argument, right? My Z doesn't care about the argument because e power 2 pi is 1, right? But log does, right? Log does. Log picks up this. Okay, it's not the same representation, right? It's something else, right? It's not e power. Log picks up what representation you are using, right? So good. So plus what should I write here? Log Z1 by B. But I can write it as log A minus log Z2 plus log Z1 minus log B. Right? Log, this can be log A by B. Okay? Plus log Z1. Okay? Huh? So, what is this? Log A by B. Let's find a log A by B. Huh? So, A is which complex number? The one below, right? So, A is some modulus mod A e power 2 pi I. Remember, I have to take into account this 2 pi I because log will pick it. Like log will pick this 2 pi. What about B? B is some mod B e power 0. Right? 1. B is just above. Its argument is, right? Okay? B is just 0. So its argument is just 0. Sorry, B is just above the real line, so its argument is 0. Right? Okay? Fine. What about this ratio then? Log mod A divided by mod B e power 2 pi I. Right? Right? I just substitute this. Right? But A and B are their modulus is same, right? Yes. So they are so close to this real axis that this length doesn't matter. So this length and this length are not roughly same. In the limiting case they are. Yes, sir. Yeah? They are same. Right? So this and this goes. Right? What do I get? Log e power 2 pi I. It's 2 pi I. Plus what is this? This is log, what is log Z1 by Z2? It's I1. Right? It's that big. I1. Right? So it's minus I1. Right? So I recover the same relation. So this implies I2 plus I1 is 2 pi I. Right? Why did this happen? Because the integral had a discontinuity. This integral had a discontinuity. That's what you were picking up. Right? When you integrate over the curve, it's that discontinuity you are picking up. Okay? So this would quite often happen. This is almost always true. Yeah, no, this is always true. Right? Whenever you have integrating, we learn that it is always true. Okay? Whenever you are integrating a complex function around an analytic complex function around a point of its where it's not analytic, okay, right? Its integrals would be discontinuous, okay, and that is the discontinuity you pick, okay. Now you see that if you take I1 and just associate it a value, okay, as if you were dealing with real functions, okay. For I2 you need to associate what? 2 pi I minus I1. So you just integrate whatever I2 the way you want to integrate, but add 2 pi I. Okay? Yes, fine. Add or subtract, and that will depend on how you are doing. Are you doing from Z2 to Z1 or Z1 to Z2? Right? Basically, you pick up this discontinuity. Right? Split your integral and then do it as if. So split your integral from here to here, and then from here to here. Right? Then it will automatically pick up discontinuity 2 pi I minus 2 pi, whatever. Okay? Is this clear? Is this clear now? That if you have one point of non-analyticity, how to associate values to like open contours. Right? This is an open contour, it's not one closed, Z1 to Z2, whatever contour, right? So there were two types of curves that you could consider, one going around 0, okay? Another not going around 0, I was able to assign values to them. Okay? Fine? Okay, good. Is this the entire story here? The answer is no. This is not the entire story. Okay? Can you please listen?
Yes.
This is not the entire story. Okay? The reason is this. What if there is some guy, okay, so your Z1 was here, Z2 was here, Z1 is here, whatever. He doesn't measure arguments from 0 to 2 pi. Okay? He wants to measure arguments from minus pi to pi. What Naveen already earlier guessed accidentally. Right? He wants to measure arguments from minus pi to pi. Minus pi to pi. Like this. Okay? He won't see a discontinuity here. Right? Like look at the argument. Below it's e power I minus some small number. Above it's also e power I plus some small number. It's continuous. The argument is continuous here. But where is the argument discontinuous?
Minus pi and pi.
Minus pi and pi. This is where it jumps, right? But that doesn't affect the complex number. Right? Complex number, the argument comes in exponential. It comes in like e power 2 pi I. Right? So it's for complex number it's irrelevant. What is it relevant? For the integral. Right? But if this guy measures arguments from minus pi to pi, will he see discontinuity in I1 or I2? Which one? He will see I1. He will also get I1 plus I2 as 2 pi I, because that can't change. Right? That can't change, because whether you pick up discontinuity here or here, the loop integral will just be 2 pi I, whether you're going clockwise or counterclockwise. 2 pi or minus 2 pi depending on how you're going. Okay. Okay. But he will associate different values to this. Right? He will associate a different value to this I1 and I2. Right? We associated with I1 we associated just log Z2 by Z1, and I2 we associated 2 pi I minus log Z, whatever, plus whatever, minus log Z2 by Z. Right? He will do the other way around. He will add 2 pi I, he will see 2 pi I in this curve. This one. Right? What do you learn? What did you learn? Right? These integrals, when you have a pole, wrong word. These integrals, when you have a point of non-analyticity, right? These are multiple values. You can associate multiple values with them. Okay? And both are equally good. Okay? We will learn that when do you take argument from minus pi to pi, okay? And when do you take arguments from 0 to 2 pi. Okay? When it comes to log. Okay? It's a choice. It's a choice. Okay? And we learn on what thing this choice depends on. Okay? Okay? For now, all you should take home message is that when you are doing these integrals in presence of a pole, right? The open contour integrals, right? Ask pole again. In presence of a singularity, in presence of a point where the function is non-analytic, okay? Ask how are you measuring your arguments. Okay? Yes. Just if you take 0 to 2 pi, you might associate different values. Okay? If somebody is asking you a question, and then he should give you, right, how the arguments are measured. Okay? We'll come back to it when we learn multi-valued functions. Okay? We'll come back to it. Okay? Yes. Okay, this completes this. Well, not really complete. I mean, this completes this, at least this part that I want to cover. Okay? Now, so since we are slowly introducing non-analyticities, right? We just introduced one, right? It's quite apt to now talk about what types of non-analyticities we can come. Right? What types of non-analyticities can come. But for that, to understand that clearly, okay, you need to understand what is analytic function more clearly. Okay?
Yes.
So far, what I had defined earlier was that if your function satisfies what? Cauchy-Riemann conditions, then call it analytic. Okay? It's not complete. this definition is not complete. Okay? All I wanted you to have first was a workable knowledge of analytic functions so that I can add more details later. Okay? Because since you understand a part of the picture, okay, now explaining the whole picture would be easier. Okay. Okay, let's go back to our definition of analyticity. See, our final goal is to understand what kind of non-analytic behaviors can come, right? For that, we need to clarify, we need to make this definition of analyticity more precise. Okay?
Yes, sir.
What did you define non-analytic points as? Points where Cauchy-Riemann conditions
Yes, sir, are not
are. But why did we want Cauchy-Riemann conditions to hold? Why did we need? We want something to be direction independent. What was that? Right? We wanted Cauchy-Riemann conditions to hold for the functions. Okay? But why did we demand it? I mean, there is a reason we demanded it. Okay? And that reason was more stressing. What was that? That was basically the derivative of the function should be direction independent. Remember? I should be able to define a derivative which is independent of direction. Okay? Going back to the change of function f of z plus del z minus f of z. Remember, this was equal to what? Ux plus iota bx times del z plus something times y. There was something in the brackets, and I insisted that if something in the brackets vanishes, okay, then I will be able to define a derivative which is direction independent. Okay? Okay? So I will be able to define this thing. Limit del z approach to 0, f of z plus dz minus f of z equal to call it, let's say, f prime of z. Okay? Yes, sir. And what this setting this to 0, what it gave us? What it gave us? Cauchy-Riemann conditions. Right? Setting this gave to 0. Okay? Right? Now you will see that this statement is not completely right. Okay? In fact, it's the other way around. We should have defined this. Okay? We should have defined this first, this thing. Okay? And then insisted that this is direction independent. Okay? Then the other guy would have followed. Okay?
Yes, sir.
Right?
Yes, sir.
Okay? I'll come back to it, but defining a derivative for a complex function, like this guy. Right? So my goal now is to define a derivative for the complex function. Okay? Let's come back to this later on. Okay? So for that, I have to define what does this mean? Limit delta z going to 0. Delta z is a complex number. Right? I didn't even define that for you. You guys just intuitively assumed, extended it somehow. Okay? And I worked with that. Right? And a part of the picture was clear to you. Right? And we learned a few things. But now let's make this more precise. Okay? Right? So, to define this derivative, I first need what? A notion of limit. Right? Because I didn't even define limits for a complex function. Okay? Let's first do that. Okay? Let's do that. Now, how did you define limits for a real function? How did you define limits for a real function? Right? When does this limit exist? Limit x approaches to, let's say, x naught f of x. When do we say this limit exists?
Left hand limit.
Exactly, left hand limit is the same as
Right hand.
So this guy exists only if limit x h approaches to 0, you take f of x naught and a small number to it, and then take h to 0. Right? This should be same as limit h tends to 0, f of x naught minus h, right? But h should be what? Positive. Only then this will become left hand, right hand, right? So h should be 0. Right? Okay? Okay? Is this fine? Huh? Only then. Why did you check only left hand and right hand limit? Because the functions were defined on a real line. And there were only two directions to approach a point. This way and this way. Right? Huh? But what for complex numbers? Right? For complex numbers, the functions are defined on a complex plane. Right? So how many ways can you approach a point? Let's say there is a point z naught here. How many ways? Infinitely many ways, right? And let's quantify these infinitely many ways, right? So I can approach a point through this direction, let's say theta, right? By taking a complex number like this, z naught plus h e power I theta, h is positive, right? So as h approaches 0, my complex number, let's say z tilde, approaches what? Z naught, right? And theta defines my direction on which I am approaching this, right? This is clear, right? Z naught h, because let's say this is my h from here to here, this length is h, then this complex number is what? Right? This complex number, this z naught right? Plus h e power I theta, just like vectors. Okay? This guy, this vector plus here one. Okay? Okay? So now that we have quantified the direction of approaching a point, then infinitely many of them, theta takes continuous values from 0 to 2 pi. Right? Now let's define the limit. Okay? Now, the limit, what did we define the limits for real function? The left hand limit and right hand limit should be same. What should be here? No matter how you approach this point, z naught. Yeah, exactly, it should be direction independent. So limit z approach to z naught, okay, f of z should not depend on direction, okay, which means limit h equals to 0, f of z naught plus h equal angle theta should be independent of what? Direction. What quantifies direction here? Theta. It should be independent of theta, right? There should be no theta. Once you do this operation, there should be no theta, right? There should be no theta. So if you just do this operation and you get something, let's say f naught, okay, f naught, then you say the limit exists. Okay, just like here, when you do this operation and both the things give you same answer, small f naught, right? Then you say the limit exists. Okay, remember the same thing you learned in real functions. Okay, I hope this is clear to you. F naught, right? F naught may not be equal to the function evaluated at x naught, right? It may not be equal to function evaluated at x naught, right? The function may be completely ill-defined for x naught. It may be of 0 by 0 form, right? But the limit would still exist. Okay? Limit would still exist. Let's do an example, a complex one and a real one. Okay? Let's take f of x equal to x squared minus 4 divided by x minus 2. Okay? Huh? Now what is limit x approaches to 2 f of x? This thing you should answer. Okay? What is this? It's 4, right? Is it? It's 4, right? So how did you do? So I do limit h equals to 0, f of where I am checking the limit at 2, x equal to 2, right? So 2 plus h minus f of 1, 2, right? Oh no, what am I doing? Limit 2 plus h the whole square minus 4 divided by 2 plus h minus 2, right? This is checking the upper side limit, right? But h is positive, huh? Remember h is positive. Okay, what is this guy? Since h is, your you're taking h anyways to 0, so h is very small, right? You can ignore h square. You can ignore h square, h cube, any higher powers of h. But you have to keep h. You have to keep h to the power 1 because the numerator, the denominator has h. Okay? That's why you have to keep h. Okay, what is this? 4 plus h square plus 4h minus 4. This 4.
Yes, sir.
This is a plus b compound square. And this 2 and 2 will go. Now this 4 and 4 will go. H square I ignore because I am working with this. And then what do I get? Limit h equals to 0. 4h by h, which is 1. H goes, so this is 4. H0 disappears. Right? Because there is no h. Or you could have kept this h square, it will anyways disappear. Right? Because h goes to 0.
Yes, sir.
Right? So it turns out that this limit is 4. And if you do 2 minus h, everything will be the same. Right? 2 minus h, you will get minus 4h. Right? Huh? Divided by minus h, there will be 2 minus h, minus will go, you will get 4 again. Right? So top limit and bottom limit are same. Huh? Let's take the same function, but now treat it as a complex variable. Huh? F of z, z square minus 4 divided by what? Z minus 2. But now it's more, right? You don't have just two directions, you have infinity, right? To quantify that, what do? We take, to check the limit, what do we do? Limit, right? H equals to 0. Right? At what point? Z0, what is my Z0? 2. I am checking the limit at 2. So 2 plus h e power I theta minus 4. 2 plus h e power I theta minus 2. Okay? Right?
Yes, sir.
Now what does this give? What does this give? Right? 2 and 2 will go. Right? Huh? And what do I get? Limit h equals to 0. 2 square is 4 plus h square e power what? Minus 2i, sorry, plus 2i theta plus 4h e power I theta. Okay? Minus 4 divided by h e power I theta. And this 4 and 4 goes. Okay?
Yes, sir.
Now h, once 4 and 4 goes, h cancels one factor from your limit h equals to 0. H cancels, right? H e power I theta plus 4. When I put h to 0, it just gives me 4. Does this depend on n theta? Is this direction independent?
Yes, sir.
Right? No matter how I approach this point, right? Okay? Huh? This guarantees. This is guaranteed to be 4. Right? Huh? So this function, right? This limit z equals to 2, z square minus 4 divided by z minus 2 is what? Well defined. Right? Okay?
Yes, sir.
When this limit existed there, what did we call the function to be? Continuous. Right? Right?
Yes, sir.
We call the function to be, provided the function is well defined
Also, well.
at the value, right? This limit is equal to f of z, right? Obviously, this function is not well defined at z equal to 2, right? But I am saying, what I am saying that this limit, okay, this limit was 4, right? If you were doing some limit of some other function, limit z equals to 2, f of z, and it turned out to be f of 2, right? Okay, some other function, okay? Then you will call this complex function to be continuous. It's sort of the extending the notion of the continuity to what? Complex functions. Right? Analytic is not. Right? Today we are defining analytic functions in a bit more precise manner, so that we can talk about what kind of non-analyticities can occur. Can occur. Okay, good. So now I have extended the idea of limits. Right? Remember, one by one we are extending these ideas, right? We integrated, we differentiated a bit vaguely, but we did. Right? And now we have extended the idea of limits. Right? And a natural extension. Right? In real life, you were able to approach two directions. On the complex plane, you were able to approach from any direction. And for the limit to exist, we want every direction should be the same answer. Okay? Good. Now, since my definition of limit is clear, I can give a clear definition for derivative now. Okay? A function f of z, a complex function f of z, okay, is said to be differentiable. Is said to be differentiable if this limit exists. Limit delta z equals to 0, f of z plus delta z minus f of what? Z equal to delta z. If this limit exists. Correct? So what do we mean when we say delta z going to 0 and this limit exists? Right? What do we mean? That it should be directionally independent. Right? In other sense, the derivative should be direction independent. Remember that statement earlier, now basically reduced to this limit should exist. Right? That would guarantee that no matter what direction you take the derivative in, you will get the same answer. Right? Okay? Right? But okay, so this we can do like this. So delta z, so I can do like this, h equals to 0. Right? F of z plus h equal I theta minus f of z divided by delta z with h equal. This thing should depend. This thing should be what? What does that mean here? Functionally, what does it mean? Here, it exists. The limit exists here, true. But what would you look for when you compute this object? Right? When will you conclude that it is directionally independent? When it's independent of what? Theta. When it's independent of theta, because theta is the direction you are approaching. Right? It should not depend on theta. Okay? Then the function is called, obviously real functions we call them differentiable. What should I call this thing? No, not yet. We didn't reach analytic yet. We didn't reach analytic. We're just now understanding how functions, complex functions are differentiable. Right? We'll call it differentiable. Right? Real function we call it differentiable. But what should we call this? Complex differentiable. Okay? This notion of differentiability is well defined on a complex plane. So we call it to be complex differentiable. Okay? So a function is complex differentiable if this limit exists. Okay? Okay? So do you understand now complex differentiability now? Do you understand this, right? Yes. Okay? Complex differentiability means this limit should exist. Which means operationally, okay, when you actually go and do it, this should be independent of theta. Compute this, and this should be independent of theta. Okay? This is one way of computing, right? You took delta z to be h equal I theta and you progress towards h. Okay? You can also use delta x, delta y to do it. I find this simpler. Okay? Good. Okay? Okay? Now, let's see what the problem was with our thing when we demanded Cauchy-Riemann equations to hold. And then just vaguely said, okay, now the function is independent of, no. Yeah, we said complex and analytic, we'll see this, that's also not complete picture, okay? But we said that if Cauchy-Riemann equation hold, the function is complex differentiable, right? In the sense that the derivative is direction independent. Okay, what was my f of z plus z plus delta z minus f of z? What was this guy? It was ux plus iota dx, right? Times delta z, okay? I divide by delta z. Okay. Plus what? Delta y times something, and it didn't depend on deltas, right? It was something h. Okay? And setting it to 0 gave me Cauchy-Riemann, right? Divided by delta z. This guy. It was this guy, right? I just divided by delta z. Whatever change we had there. No? Now shall we take the limit? Now taking the limit delta z going to 0. Okay? This guy, this part, there's no delta z here. Right? So the limit will apply here, where? This, on this guy. Delta y by delta z. Right? Because there is no delta z here also. Right? In this bracket. It's just partial derivatives inside this bracket. I don't remember the factors, that's why I'm not writing it down. Okay? But it just contains what? Partial derivatives. Right? It's independent derivative. So all we had to look for was this. All we had to look for delta z going to 0, delta y, right? Delta z. This is the only thing that matters in this, right? Okay? Now, what does this do? What is my delta z is what? H e power I theta, right? Remember? What is delta y? It's also equal to delta x plus I delta y. What is delta y? It is h sine theta, right? H sine theta. And what is delta z? H e power I theta. Remember? Delta z going to, sorry, and now h going to 0, right? Right? This is equal to this. This limit, well, not strictly. I mean, I have to check. This means that check there that this is independent of theta, right? Is it independent of theta? No. Right? No. Because you will get h will cancel, it will be sine theta by e power I theta. There is no way this will disappear. Right? That's why we wanted this to go away. Right? This thing. And that gave us what? Cauchy-Riemann. Okay? Right? Because if this thing is there, then for sure your function is not complex differentiable. If this thing, if Cauchy-Riemann conditions do not hold, it means this thing, right? Cauchy-Riemann condition, if you remember, ux is equal to dy, uy equal to minus vx. If these things do not hold, right, then for sure you will have theta dependence because of this sin theta by e power I theta, right? Right? If you want a possibility of complex differentiability, make sure this thing vanishes. You have CR, right? Remember, a possibility of complex differentiability, right? Because if this thing vanishes, right, I still have to deal with this, right? Okay? If Cauchy-Riemann conditions hold, and these partial derivatives are nice, continuous, and all, right? Nice, continuous in what sense? In the sense of, yeah, right? In the sense of, right? But they should not just be continuous at this point. They should be continuous. Right? No, not close. Just in the, so you have z, right? When you compute these partial derivatives, they should be continuous in some part of some small region, right? Because you want in every direction these guys give you same. Right? Yes, sir. Right? Right? Okay?
Yes.
Right? Because ux equal to iota vy, right? There is y also, right? You're taking this at a constant y. Right? Yes. So I can set that y to be, so there should be some small neighborhood of this point, with some small region, no matter how small, where these guys should be continuous, well defined. Right? Only then you will have complex differentiability. Okay? So what did we learn? If Cauchy-Riemann conditions do not hold, then for sure my function is not complex differentiable. For sure. Right? If they hold, then there is one more condition, but usually in physics this condition would be satisfied. If they hold, right? If they hold, then okay, provided this extra condition, right? These partials should be right continuous, well-behaved functions around this point where you check. Okay? Only then you will have what? Dational independence. Right? Right? So if you want your derivative to exist, Cauchy-Riemann plus this extra condition. Okay? Not just Cauchy-Riemann. Right? I didn't want to put so many details in your head directly in the first class. Okay? But now you can handle it pretty. Is this more clear? Yes. This is just one part of the picture more. Okay? We didn't reach analyticity yet. We didn't reach analyticity. Okay? Let's try to do some functions. Okay? Let's do mod z. Okay? Let's try to differentiate this. Okay? So how do I differentiate? What limit should I take? Limit. Let's do it z equal to 0. Z not equal to 0. Okay? What should I check? What should I check? Yeah. Okay. So limit delta z approaches 0. Mod z naught plus delta z. But z naught is 0. Then this mod delta z. Okay? Minus what? Mod z naught, which is just 0. Okay? Divided by what? Delta z. But what does this mean operationally? That this is check. h equals to 0, mod r equal I theta divided by what? R equal I. Right? This thing should be what? Independent of theta. Right? What is mod r e power I theta? It is r. Right? E power I theta ka mod is 1. Right? Isn't it? Mod is just mod a b is mod a into mod b, right? Mod e power I theta is just 1. Right? So what do I get? Oh no, r. No, sorry, this should be h. H. Right? Remember the definition? Okay. Then what do I get? Limit h equals 0 e power minus I theta. This guy survives. Right? Mod gets rid of this guy. Okay? What do we get? What do we get? This is just e power minus I theta. Right? Is this independent of theta? Huh? Is this guy independent of theta? Huh? This guy independent of theta? It is independent of theta. Huh? This guy is independent of theta.
It is dependent. It is dependent.
It is dependent. Sorry, I misunderstood. Okay, sorry. So it is what?
Dependent.
Dependent on theta. Right? Huh? Oh, so sorry. Okay. So therefore, does the derivative of this function, is this function complex differentiable at z equals 0? No, it is not. It's not. Right? This function is not complex differentiable at z equals 0. Right? Huh? What about this? What about yeah, no. Yeah, no, okay, what about question 1? What about question 1? What about CR equation? Okay, so this is not okay. Good. What about question 1 equations? I don't know. So then square root x squared plus mod z is 1 square root x squared plus y squared. Right? So what is u plus what is v? V is 0. Right? So v is 0. Let's just check. I don't know what question 1 is. And u is what? Square root x squared plus y squared. What is ux? 1 by 2. 1 by 2 what? Half 2x divided by square root x squared plus y squared. But we are working there at x equals 0. Right? Right? At x equals 0 and y equals 0. Right? Huh? X equals 0, then it just goes to 0. Right? But these are not well defined. Yeah? Yeah? We'll give a better example maybe. Right? Okay. So sort of question 1, the question 1 conditions, will it be 0 by 0? Well, okay. This question, okay, good point here. If my y was away from 0, so we are working with 0, right? Right? Okay. Let's say my y was here, a bit away from 0, not really 0. Then what is ux? 0. No, it's not 1, 0. Right? If my y was slightly away from 0, right?
Yes, sir.
Huh? What is vy?
0.
It's just 0. Right? So ux is equal to vy at this point. Right? If my this is slightly away, right? So around this point, no, but then it should be equal to add 0. No, sorry, it's not well defined. Right? It's not, the partial derivatives are not well defined there. Right? Because it will be 0 by 0. Right? 0. X approach to 0. Yeah, it's not well defined. Maybe I have to think, huh?
0 by 7. It will be 0.
No, if y is slightly away from 0,
0 by 8.
so if I take x going to 0 first, okay, then it's just 0, right?
Yes, sir.
Then and vy is also 0. If I take x going to 0, right? Just x going to 0. But provided y is slightly away from 0. Right? So if I take x going to 0 first and then I take y going to 0, then ux is equal to vy. Okay? But provided I have this order of limits, x going to 0 first and then y going to 0. Right? Huh? But then if I take y goes to 0 first, right? Then it's just 1.
Yes, sir.
Right? Then it's just 1.
Yes, sir.
So this is not well defined. The partial derivatives are not, the limits of partial derivatives are not well defined. Right? You have to fix the order. But yeah, maybe I shouldn't have Maybe I shouldn't have done this example. Yeah. Okay, what about the other one? Uy is just, you'll get once again same problem, right? Y square plus y square. And what is dx? That's also 0. You see, these partial derivatives are not well defined around that point, right? There is a way you can define them, right? Then the Cauchy-Riemann equations will hold, right? Cauchy-Riemann equations will hold, right? If I let's work with this definition. Let's say we work with this definition. Then I take x going to 0 first, right? No, but then okay, if I take x going to 0 first, this will be 0, but this will be 1, right? This will be 1, right? This one. If I take x going to 0, this will be 1. Okay, you can't make them satisfied. So I thought I can make the Cauchy-Riemann equation to be true there, but the function would still not be. Yeah, let's save it. Let's save this. So, okay, but you see, this function is not. Okay, this guy. The reason you got this weird thing, right? If you go one way, right? If you go one way, like if you take delta x going to 0 first, and then delta y to 0, you get different answer than taking delta x to 0 first and delta y to 0 first. Okay? Huh?
Yes.
Right? It's because why? The function is not complex differential. Right? It's a theta dependent stuff. Right? And this sort of gives you some, okay, we messed up, but we learned something out of it. Right? Huh? Okay? We considered this and we were not able to understand, but we learned something out of this. What? That when you are dealing with non-analytic functions, right? When you're dealing with what? Complex differentiable functions, right? If it's not complex differentiable, right? Then what? Then whatever limits you take, they'll depend on what? Do you take delta x to 0 first? Do you take x to 0 first? Do you take y to 0 first? These things will matter, right?
Yes, sir.
Okay. Right? If you think of these functions as functions of x and y instead of this complex variable z, so it means there the limits on whether you go take x to 0 first or y to 0 first, those things will matter. Okay, you just saw. Right? Okay. Good. Yeah. Okay. Maybe I'll rethink about what I said here. Right? Okay. Okay, good, but what should the punchline here? That the mod z is not complex differentiable. At what? At z equal to 0. Right? In fact, it won't be complex differentiable at any z. Even if you go away a bit, probably it won't be. Most likely it won't be. But check, right? Check the thing. Okay, let's do mod z square. Okay, let's do mod z square. Okay. What do I need to do? Limit h equals to 0 mod of z naught plus h e power I theta minus mod of z naught. And this is my function for each square. Right? Okay? Divided by what?
Yes.
H e power I theta. Delta z, which is h e power I theta. Okay? Huh? Okay. Where should I do it? I'll do it at z naught equal to 0. Okay. I'll do it at z equal to 0, then we can let's look at z naught equal to 0. Okay? Let's look at z naught equal to 0. What do I get? Limit h equals to 0. This will go away, right? Z naught is 0. And then what do I get? H square. H square e power 2 I theta divided by h e power I theta. But there is a mod, so e power 2 I theta will go. There was a mod, right?
Yes, sir.
H is positive, so mod doesn't do anything to it. And you are anyway squaring h. Right? One of the h's will go, and the limit h equals 0, h e power minus I theta, right? What is this guy? It's a 0. Right? Is it independent of theta? Yes, it is. It is independent of theta, right? Huh? So that means this thing is what? Complex differentiable. At what? At z equal to 0. Huh?
Yes.
This thing is complex differentiable and at z equal to 0. Good. Huh? Nice. Okay. So so mod z square is complex differentiable at z equal to 0. Okay? Okay? So it means Cauchy-Riemann equation have to be true. Okay? at z equal to 0. So that automatically implies Cauchy-Riemann equations are true, right? And it also implies another thing, that these partial derivatives at 0, where it is complex differential, are they nice continuous, right? Okay? Right? Huh? Okay?
Yes, sir.
Good. Good. But what about like any point which is not 0, but any point close to 0? Right? This is z naught. In fact, let's consider any other point. Mod z naught limit h equals to 0 plus h equal I theta minus mod z naught h equal I theta. Okay? Okay? Good. Okay. Now, what is this doing? What is mod z square? It is z bar. Yes? Z bar. So it is z naught plus h equal I theta times z naught star plus h equal minus I theta. Okay? Minus what? Mod z naught square. Divided by what? H equal I theta. What does this give? Can you please multiply? Can you please multiply? That will go, and I will get h square plus I will also get z naught h equal minus I theta. I will also get what?
2zh.
No, 2 z naught h equal minus and z naught star h equal I theta. Is this fine?
Yes, sir.
Right?
Yes.
Okay. One of the h's will go, right? Limit h equals to 0. I can cancel one h everywhere. So h plus z naught equal minus I theta plus z naught star equal I theta divided by what? Or divided by nothing. Or equal I theta. Okay. We can divide by equal I theta, so this will go. This will go equal minus I theta, this will go 2 I theta, and this will go. Okay, this is equal to this. Right? Huh? Just check the answer, right? You probably, I think I have done it correctly. What do I get now? If I put h to 0, what do I get? Z naught equal minus 2 I theta plus z naught star. Right? This is that limit, right? The limit for complex differentiability at some point z naught. Right? Huh? When is it independent of theta? Only at z naught equal to 0, because then this will vanish. This guy will vanish. Right? And you will get 0. Right? But otherwise, at any other point, no matter how close you are to z naught, this depends on what?
Theta.
It depends on theta. So this function mod z square, is it complex differentiable at z equal to 0?
Yes.
Yes. At any other point? No, it's not. It's not. It depends on theta. Okay? Huh? Right? Huh? Okay. But there are two ways you can approach this. Okay, there are two ways you can approach this point. There are two other ways probably where you can approach this point. See, that is theta equal to 0 and theta equal to 2 pi. Right? See, this depends on theta, but it takes the same value when theta is 0 and theta is 2 pi. So it means this is your z naught. If you approach this way and if you approach this way, right? So this is h equal I theta, right? Remember, this is the complex plane. This is theta, right? This is the direction you are approaching this point. Right? So if theta equals 0 is approaching like this, right? Theta equal to 2 pi is approaching
Like
this, right? This takes the same value. Theta equal to 0 is z naught plus z naught star. Okay? Right? Theta equal to pi is what? Equal minus 2 pi I, right? Which is just 1. Still z naught plus z naught star. So this way and this way, it is the same, right? So this function is not real differentiable. Right?
Yes, sir.
Which is indeed true, because this function mod z square is just x square plus y square. This is a nice function. It's differentiable. It's a real function. And it's differentiable. And that's what you see. Right? But it's not complex differentiable. Do you get point?
Yes, sir.
And that's why we need a different word, complex differentiability. Right? Right? But if I had said it is differentiable, right? Right? So that would have been in the real sense. Okay? This function mod z square is differentiable, right? At any point z0. Right? But it's not complex differentiable at a point where? At any point except z equal to 0. Right? So do you understand this one? So at theta equal to 0 and theta equal to 2 pi, what do I get? z0 plus z0 star, right? Which is just what? 2x. Right? Which is indeed what the case. Differentiate this with x, it's 2x. Right? Right?
Yes,
Because you're checking this way. Right? You can also check that it is same if you approach along y, and you will get some 2 out of y or something. 2y, sorry. You get some 2y or something. Right? Which is indeed this way. Because you are approaching along vertical direction, keeping x equal to constant. This you are approaching what? Horizontal direction, theta equal to 0 and theta equal to pi. Right? You are keeping what? Constant y. So that should be equal to partial derivative. Right? Remember?
Yes, sir.
Right? Hello?
Yes, sir.
So, but for any arbitrary theta, this takes different values.
Yes, sir.
Okay, good. Even theta and minus theta are not same, right? E power 2i theta, e power minus 2i theta are not same. They are complex conjugates of each other. Okay, nice. Yeah. So this is not complex differential. What? As z equal to z not equal to 0, it is complex differential. Okay. Now we are in a position to define what? What do we actually mean by analytic functions? Right? The bigger picture. Okay? The bigger picture. Okay? A function, I was too loud with this function. A function f of z, it's said to be analytic. Okay? It's said to be analytic at z equal to z0. Okay? If it is complex differentiable at z0, so it should be complex differentiable at z0 and in a small region around it. Okay? So it should be complex differentiable at z0 as well as in some small region around it. Okay?
Yes, sir.
Okay?
Yes, sir.
Is that fine?
Yes, sir.
So if I take some small region, no matter this small region, okay, is up to you. No matter how small, just find some small region, okay? Find some small region around this z0, okay, where it is what? Complex differentiable, but it should including z0. It should be complex differentiable at z0 also. Okay? I need to check how much better is it. Yeah. Right? So not only z0, but what?
Small region all around that, including
Small region around z0. Okay? Good. Right? So it's not just Cauchy-Riemann. It's not just Cauchy-Riemann. Right? But if Cauchy-Riemann equations do not hold,
the function is surely
non-analytic. The function is surely not analytic. Right? But if they hold, you have to check other things. Right? You have to check other things. But in principle, you should just check complex differentiability. If complex differentiability is there, Cauchy-Riemann equations will hold that. Right? Yeah. But yeah, physics, I mean, just check Cauchy-Riemann, okay? I mean, you won't get crazy functions, basically. Okay? There would be functions where Cauchy-Riemann will hold at a point. Okay? At a point, there would be functions where Cauchy-Riemann will hold, then the function will still not be analytic. Because what? It won't be complex differentiable. Right? Because the partial derivatives won't be continuous, won't be nice. They would either blow up or something. Right? Just like we saw. Okay? So is the complete picture of analytic functions clear to you? Okay? Let's take this mod z square. This mod z square. Right? Is it complex differentiable at z not equal to 0? Yes. At this point? Huh? Is it? Yes. We just checked. Huh? Is it analytic at z not equal to 0? Can you find a small domain around z not equal to 0 where it is complex differentiable? It's small region. No, because this function is analytic. Complex differential only at z not equal to 0. The moment you would move even a bit, you will 10 to the minus 500, 10 to the minus 6000, whatever. You just move a bit, the complex differentiability goes away. So this is an example which is complex differentiable at a point, but still not analytic. Still not analytic. Okay? Is the definition for analyticity clear to you?
Yes, sir.
Huh? Okay? So this is the definition, real definition of analyticity. Yeah? But when you are working, just check question 1. Okay? Check question 1. Right? If question 1 holds, it will most likely be analytic. Okay? Most likely be analytic. Most physics questions, it will most likely be analytic. Right? But yeah, if you are doing mathematics, you can sometimes get some crazy functions. You might need to deal with some crazy functions. Okay. One such function is, I think e to the power minus 1 by z square. I think this. No, something like this. Of z is this. I don't know. I'm trying to remember from ChatGPT. I shamelessly put this in ChatGPT. Give me an example of a function, and it give a crazy example. Something like this. F of z is this, and then at z equal to 0, it's 0. Okay? At z naught. Something like this. Okay? But I will check again, and then we'll work it out. We'll work it out. Okay? Huh? Right? Okay. So in this function, assuming this was the same function that ChatGPT gave me, okay? This function, I was able to show that it has the Cauchy-Riemann equation hold.
But it is not analytic.
The Cauchy-Riemann equation hold, but it's still not analytic, right? But we give an example, right? This guy. There was another certain thing here. Yeah. Sorry. The thing about this function, the Cauchy-Riemann equation was hold, the function was still not differentiable. The Cauchy-Riemann equations were correct, right? It was still not differentiable. And the reason was that partial derivatives were not continuous. Or if you just forget about everything and just check whether the derivative is indeed direction independent, okay? You will find that no, it's not. It's not. Yeah. Okay? So this is the full definition, right? The more precise, not more precise, the precise definition of analyticity, right? So what is an analytic function?
He said differentiable at a point and in a small region.
It's a small region. It doesn't matter how small the region is. Okay? It doesn't matter. Okay? Is this fine? Is this okay now? So now the definition of this is complete. Now that we understand analyticity very well, okay, let's try to identify what kind of what kind of non-analytic stuff can come in. Okay? Right? So you can destroy analyticity at a point, okay, depending on how the things around it are. Okay? First kind of non-analyticity that can come is called singularity. It's called singularity, isolated singularity. So this is classification based on how if you have a point of non-analyticity, what's going around in its neighborhood. This kind of classification. So isolated singularity is okay. Isolated singularity. Okay. This happens when a function is not analytic at a point. Okay. But it's analytic in its surrounding, in its neighborhood. An example is just 1 by z. F of z. This is one example. At z equals 0, it's not analytic, right? But you can construct some small region around z equals 0
Where it's analytic.
where it's analytic. Okay?
Yes.
Okay? z equal to 0, and what? Where? Z equal to 1. Right, 1. No, this guy goes here. So you were already able to guess, right? What were you able to guess? That this is a point where the function just blows up, right? Where the function just takes infinite value. It's not well defined on a complex plane, right? Because there is a point in the domain whose image is infinite, which is not in the range of the function. It's not in the range of it. It's not on the complex plane, right? Right? It's well defined for a extended complex plane, though. Okay. Good. So it has two isolated singularities, right? Why isolated? Because I can find a region around z equal to 0, in fact a very big region, where the function is around that point. Okay? Huh? And what about this? I can still find a region, right? So this is called isolated singularity. Okay? Huh? But it has three types. It has, I just showed you one of the types. Okay? So first is called something I was accidentally saying out. It's called a pole. Okay? Huh? So isolated singularity is what? The function is non-analytic at a point, but it's analytic in its neighborhood. Right? Okay? See, the function is not analytic here. Right? What if I consider a small point which is very close to it? Right? Then you can ask, okay, it's not analytic here, but what about a point very close to it? Right? What happened?
Low bit.
How much battery is there? 10. Huh? That should be enough. That should be enough. That should be enough, hopefully. Yeah? So, you can ask, please, focus here. It's okay, let it be. I mean, even if it's not recorded. If a function is analytic here, okay? But you can ask, what if I consider a point very close to it? Because remember the definition of analyticity, the function should be complex differentiable at a point, not just at the point, and its surrounding, right? So if I consider this point of non-analyticity, what if I consider another point so very close to it? They are like, I can still define a surrounding, right? I take this complex number, add this complex number, divide by 2, and this is the surrounding, right? You can always find a complex number between two numbers. That's why this idea works, right? Because you add the two complex numbers and divide by 2, right?
Yes, sir.
Z equal to 0. Z by 2 will always be in between the 2, if this is Z. If, let's say, this is 0. Right? So it's okay, it's perfectly a good idea, right? There's nothing wrong with this, nothing ambiguous with the idea. The function is non-analytic at Z equal to 0, but it's analytic in its neighborhood. Right? Right? That's an isolated singularity. It has it has three types. First one is a pole. Okay? Huh? If the function, okay, what happens at an isolated singularity? But typically the function just blows up. The function just blows up. First, it means if you move close to the point, right? If you move close to the point, the function takes very large values. Huh? Huh? If around that point the behavior of the function is 1 divided by, let's say z0 is my isolated singularity. My isolated singularity is at z0, right? If around that point, if you investigate the behavior of the function around that point, if it is z1 divided by z minus z0, raised for n, raised for where n is any integer, 3, 4, 5, whatever, right? Then it's called a pole. Then it's called a pole. N is any integer, it should be finite. It should be finite. Then it's called a pole. Remember, function can have different behaviors around different points, right? For example, sin x, it has a different behavior around x equals 0. It's approximately x. Okay? It's approximately x. Around some other point, it will be something else, probably. Right? The function can do crazy things at different points, but around a certain point, its behavior might be something else. Right? So I'm just looking at the point in the neighborhood of what? Z0. It should be like this. Okay? We'll later on figure out how to figure out. We'll figure out how to figure out that the behavior is this. Okay? Huh? Okay. So this is called a pole, but pole of order n. Pole of order n. Pole. So f of z around z0 should be approximated by this, and it's called pole of order what? Pole of order n. Okay? When n is equal to 1, then it has a separate name, it's called simple pole. Okay? So for n equal to 1, it has a different simple pole. Okay? Is it fine?
Yes.
Simple pole, right? So we'll know what kind of non-analyticities can come. Okay, this is one. Okay. And examples you know, right? This is like it has two simple poles. Where at z equal to 0 and z equal to 1. Excellent. Okay. What about this guy? 1 divided by z minus 1 square. What about this guy? So right now I am just taking the function to be this, right? So this is an obvious pole. What? Where z equal to 1. What order?
2.
Order 2. Order 2.
Yes.
Okay. What about 1 by sin z? What about 1 by sin z? Z equal to what? Z equal to what? 2 n pi. No, n pi. Right? Sin 0 is 0, sin pi is also 0, n pi. So it has how many poles? How many poles does it have? Infinity. Right? But all of them are isolated. They are separate. They are away from each other. So it might not be here the poles are obvious, but sometimes they are not obvious, right? What about any polynomial f of z equal to 1 divided by p of z, where p of z is a polynomial function? Right? What about this? How many poles will it have?
Power depends on.
It depends on the degree. Right? Right? And all of them will be simple poles. Right? Simple poles means order 1. Unless two roots are same, right? Then you will get 1 divided by z minus alpha per square, and alpha is the root which repeats.
Yes.
Then you will have pole of order 2 and rest of them will be of order 1.
Simple.
Right? Okay, good. So this is pole, right? Right? Okay. Good. So this is one kind of similarity. Okay? The pole. So this is one kind of isolated similarity. Okay? There is another kind of isolated similarity. This is called essential similarity. We'll learn more. Okay? This is the worst kind of similarity. Okay? This is the worst kind. Okay? This is the worst kind. So let's say this is the kind in which the function, let's say at z equals z naught we have the isolated similarity, which is an essential similarity. Okay?
Yes.
It means the function around that point can be approximated by this, and thus from 1 to infinity 1 divided by z minus z naught raised to times some number times some number. Okay? Some number which is better. Let's call it. What? Everything okay? Should I stop? So it's something like this. Okay? What is the difference? There, right? There is a finite 1 divided by z minus, the approximation is finite. Right? 1 divided by z minus z naught raised to q. Here you have the sum of infinite terms. Right? Which is very different. Do you get the point? Right? If you add 1 plus z square, it's a polynomial. Right? But if you add 1 plus z square plus z cube, right? It's not a polynomial. Right? Okay?
Yes, sir.
Okay, in fact, 1 plus z square plus so on up to infinity is 1 divided by 1 minus z. Right? GP, limited progression. Right? Provided more than is 1, less than 1. It's a completely different thing. Okay? So this infinite sum is a completely different thing. Most erratic behavior. Okay? You won't be able to approximate properly. You have to take infinite sum. Okay? It's called essential similarity. Okay?
Yes, sir.
How about this? Let me give an example. E power 1 by z. This has an essential similarity where you can just guess. It's very intuitive. Z equal to 0. Right? This is where things are like not nice. Right? In fact, I can expand it. If we will later on learn how to expand complex functions, right? Just like Taylor series. Right? Taylor series you did for real functions, right? We'll do that. We'll extend that to complex functions as well. But for now, just accept that it is what was e power x for real functions? 1 plus x plus x square by 2 factorial. Yeah, just substitute 1 by x and just extend it to complex functions. 1 plus 1 by z plus 1 by z square 2 factorial. 1 by z cube 3 factorial plus so on. So around z equals 0, can you ignore any term? You can't. Right? Right? this would be, right, exactly, this would be bigger than this would be bigger than this, but you don't know where to stop because this goes up to infinity, right? So it's better to take the entire sum, right? Isn't this like this? Some non-constants which are dependent on n, 1 by 2 factor, 1 by 3 factor, so e power 1 z has an essential similarity at z equal to 0. Okay?
Yes.
And the third one is the easiest one. It's removable singularity. What? Removable singularity. This is the easiest one. Okay? So this is that singularity. Okay? If you take the limit, if you redefine the function there, okay, then there is no singularity. If you redefine. Okay? It's not obvious that redefining a function will remove stuff. Okay? Will remove the singularity. Okay? But in removable singularities, okay, right, you can do that. For example, you just learned, in fact, you just removed one singularity, just in the beginning of the class. Limit z equals to 2, z square, how about this function, sorry, f of z equal to z square minus 4 divided by z minus 2. This function, right? What about at z equal to, it's 0 by 0, not defined, right? Not defined, right? But what if I redefine the function f tilde of z, it takes this value if z is not equal to 2, okay? If z is not equal to 2, okay? But at z equal to 2, it takes the value 4. Right? Then the function has all nice properties, right, that you need for an analytic function. Okay? So this is a removable similarity. Okay?
Yes, sir.
Okay?
Yes, sir.
Good. So removable is the easiest one. Okay? It's the easiest one. You don't need to deal with it. Right? There is no pole. Right? Z equal to 2 seems like a pole, but it's not. The limit exists. Right? And you can get rid of it. You can define this function. This is a different function, redefinition of the function. Right? At z equal to 2.
Yes, sir.
But typically people implicitly assume redefinition. They just assume that z equal to 2 is 2. But at z equal to 2, strictly speaking, it's undefined. Okay. So this was what? Isolated singularities. Okay? Singularities where, points where the function is not analytic, but in its neighborhood it's analytic. Right? Isolated, hence the word isolated. Right? I have to say something, but maybe later. Hence the word isolated. Okay, good. What now then? After that, if you believe, isolated singularity is done, what is left? What kind of other singularity can you have? Yeah, not isolated. Singularities around which you won't be able to find a region where the function is analytic. Okay?
Yes.
Is this fine? So non-isolated singularities. So this is that point, right? A, the function is not analytic there. B, you won't be able to find a region around it. Okay? Okay?
Yes.
Is this fine? Is this fine? This happens if A, your function is discontinuous. This can happen for two reasons. Your function is discontinuous. Okay? Means it jumps. Or B, there are too many, there are the poles, the function has poles, a lot of them, right? But I shouldn't call them poles. Yeah, no, the function has, I shouldn't strictly call them poles. The function has points of non-analyticities. Okay, this is better. The function has points where it's non-analytic, right? But they are arbitrarily close to each other. So close that if you take a point and you construct any small neighborhood around it, you will still capture one more non-units. So you won't be able to find a neighborhood, right? Jahan function analytic. So it won't be isolated. Okay? I'll give examples of both. Okay? What about one example where we're using log z. Right? What about this log z? It is log r plus theta. Right? Remember, for function at least the limit of the function should exist. That's the first thing, right? Complex differentiability बाद में आता है. That comes later, right? If the function itself is discontinuous, it has a jump, and even it won't be differentiable, right? Remember real functions. Function has a jump, the derivative blows up. Okay? So, what about here when you cross this? The argument above is what? Theta above is 0, right? What is below? 2 pi, right? So this has a jump. Where? Everywhere along this line. So all these points on this line are what? Points of non-analyticity. They are non-analytic. And they are such points that you won't be able to find a region. Okay? And when you find a region, don't find a region like this. No. There's a circle around it, small circle, right? Because it's so, I mean, you need, even if you find a very small region, so its shape doesn't matter. Okay? Just circle. Okay? Will you be around any point, will you be able to find a neighborhood where the function is analytic? No. Right? So these are all non-isolated similarities. Okay. This guy. Okay? Fine? We'll come back to it. And we learn that I can take this line where the argument jumps anywhere I wish. Anywhere I wish. Okay? One more choice we have already done is that if I measure my arguments from minus pi to pi. Right? Minus pi to pi. Like this. Right? Like this. Then the points of non-analytic points will be here. Here the point function will be analytic. Right? Huh? Remember this choice stems from the fact that you need multiple sheets to map log z. Remember when we did mapping of log z? We needed multiple sheets. Okay? Right? We needed multiple sheets. Right? This choice comes from the way you join them. Okay? There are different ways you can join those sheets. Okay? Right? Huh?
Yes.
Huh? We'll later on learn that this choice means you are joining them in a different manner. This choice means you are joining them in a different manner. Right? Not very different, but at least that this difference is there. Okay? And this difference. Okay? So this is one example of non-isolated similarities. Okay? So this was an example where the function has a what? A jump. Where the function has a jump. Okay? Right? Where the function, where the function has a jump, function is discontinuous. Okay? Now another is where there are a lot of points of non-analyticities. Right? Why are you guys laughing? Right? It's just 5-7. A few more minutes. Where there are a lot of non-analytic points, right? But they are too cluttered. Okay? They are too cluttered, too close to each other. Right? So close that if you take any small neighborhood around any point, you will never make it free from those non-analytic points. Right? Let me give you an example, and this is the last thing. Right? One line sine. One by sine or one by sine. Where are the points where the function is non-analytic? Where is the function funny? Right? Is z equal to what? Z equal to what? No, sorry. This guy should become 1 by z should become 1 by z equal to what? 0. No, 1 by z should become 0, but 2 pi, 3 pi, pi, right? N pi. So it means what? Z equal to what? 1 by pi. Right? So how many non-analytic points does it have? Infinitely many. Right? Z equal to 0, z equal to whatever. Z equal to 0, z equal to 1, 2, 3, 4, whatever. Okay? But let's look at this point at z equal to 0. Is it an isolated similarity? The similarity, the non-analytic point at z equal to 0. Okay? It has how many points in between? How many? Can you imagine? Right? Let me consider a small neighborhood. Something small. Right? So it's not analytic at z equal to 0. Okay? I want to show that if z equal to 0, I consider a small region. Right? I will catch at least one more analytic point. Right? Okay? Yes. Why? Because I can find a large n of n such that that lies inside this radius. 1 by n pi lies inside this.
Inside this region.
Let's say I consider r equal to 1. This is some small unit radius, right? But I can do 1 by 4 pi. That lies inside. Let me make r smaller. R equal to 0.5. I can increase n. There would be a small, there would be a, right? So will I be able to find a neighborhood around, right? Because the points are so dense there, right? I won't be able to find a neighborhood, right? So it's not an isolated singularity, this kind. Okay?
Yes, sir.
So this happens when the points where the function is non-analytic are too close to each other. So close that you won't be able to find a neighborhood. Okay?
Yes.
Okay? So this is the last thing. Okay? Right? So this covers most of the this covers what kind of non-analyticities can come. Right? This covers non-analytic. And in physics, you will just deal with these kind of non-analytic points. Okay? This is an important point that I'm making. Okay? In physics, mostly you will deal with these kind of non-analytic stuff. Right? Even not in all of them, some of them more than others. Okay?
Yes, sir.
We get the point? Yes. So how many singularity types of singularities are there? Sorry, the non-analytic stuff is there? 2. Right? Isolated, non-isolated. Isolated, how many types?
3 types.
3. What? Which one? Pole?
Essential singularity, removable.
And removable. What is a pole? The function.
The function is not analytic at a point, but in its vicinity, it's analytic.
Yeah, that's true. That it's not analytic at a point, but it is analytic. That makes it isolated. What makes it a pole? That its behavior around that point is 1 divided by z. Z minus z naught. If z naught is the point we are talking about, z minus z naught to the power n, where n is some finite number.
Pole of order n.
Yeah, that will be pole of order n. Simple n means order is 1. Simple pole means order is 1. Right? What next? Essential singularity. What is that? That you can't get 1 divided by z minus z naught to the power n behavior. You have to take a sum from n and from 1 to infinity. Right? An example is e to the power 1 by z. And what next? Removable. Removable is like you can just get rid of it. You can get rid of that singularity by redefining that function. And then what? Non-isolated. It means, what does non-isolated mean? A function is non-analytic at a point. You can find a region, no matter how small your region you take, you will always encounter more non-analytic points. Right? This has 2 types, right? Two ways it can occur. Right? One, if your function jumps, right, or discontinuous, or if your function has many points of many points of non-analyticities, but they are so dense that you will always be able to find. Right? Remember, this function has z equal to 0 is not isolated. This singularity is not isolated. Okay? But any other singularity, if I take 1 by 5 pi, so this is a point where the function is non-analytic, right? But I will be able to find a region, small region, right? Right? Because if I take the next one, that is at 1 by 6 pi. No, 1 by 6 pi will be blue. 1 by 4 pi. They are too far away, right? But if you increase n, right, these distance becomes smaller and smaller. So around 0, I will never be able to construct a region, a small region. Okay?
Yes, sir.
So that sort of are these. Okay? Now in the next class we will deal with poles. Then we will deal with poles of order n. Okay? And then we will deal with branch cuts. Then we will deal with this jump. Right? Not branch cuts. Okay? The function jump. Okay? Good. So dealing with them means how to integrate. Because you see, with integration, these points of non-analyticities give what? Give interesting behaviors, right? They give 2 pi I, right? They contribute, right?
Yes, sir.
Right? So in next class we will learn how to deal with it. Okay?
Yes, sir.
And some other stuff. Okay? Bye.